In this tape, we will review some of the functions and their graphs that we have previously studied and look at some new ones. Let's start with a very simple function, the constant function. This would be a function of the form y or f of x equals k, where k is some constant. For example, we could have y or f of x equals 4. The graph of a constant function is, of course, a horizontal line. For example, y equals 4. The graph is a horizontal line 4 units above the x-axis. Here we have the graph of this particular constant function. Notice that the domain of this function is a set of all real numbers. Okay, but the range consists of only the number 4. In other words, any x value can be substituted into the function. The only y value that comes out, however, is 4. Let's move on now to linear functions. A linear function is one of the that has the following form: y or f of x equals, say, ax plus b, or very often we think of it as mx plus b, where a and b are constants. The graph of a linear function, of course, is a straight line. You know that when we see this y equals mx plus b, we know that m, or in this case a, would be the slope of the line, and b would be the y-intercept. Okay? So let's look at a specific example. Y equals 2x minus 1. Okay, a linear function. And of course, we know that if the graph is a straight line, 2 points determine a straight line. So we can say when x equals 0, y is equal to minus 1. And when y equals 0, x is equal to 1/2. And we have something like that. As a special case of linear functions, we have the identity function. Okay, a special case of linear function, we have the function y equals x. Okay, a is equal to 1 and b equals 0. This is known as the identity function. The graph of the identity function, of course, it's a straight line. It goes through the origin. It goes through the point when x equals 1, y equals 1. When x equals 2, y equals 2. It is the line which bisects the first and third quadrants. Okay, called the identity function since it associates with every x value. Okay, in other words, the same value. X equals 1, then y equals 1. X equals 2, then y equals 2. This function assigns every number to itself. It's called the identity function. It's a special case of a linear function. Moving on, we come to quadratic functions. This would be a function having the form y or f of x equals ax squared plus bx plus c, where a, b, and c are constants. A is not 0. If a were 0, of course, this would reduce to just a linear function. So we'll assume that a is not 0. The graph of such a function is a parabola. Let's look at a specific example. Okay, y equals x squared minus 2x minus 8. Of course, we have, in an earlier videotape, sketched parabolas in detail. Let's just go over some of the key points. We know that intercepts are very convenient to have when we are sketching the graph of a parabola. So if x equals 0, we get y equals minus 8. Okay, similarly, we would want to set y equal to 0 to get the x-intercept. If y is equal to 0, then x squared minus 2x minus 8 equals 0. Okay, and this can be solved by factoring this quadratic equation. We're looking for two numbers which multiply to minus 8 and add to minus 2, and they are minus 4 and plus 2. Checking this by FOIL, x squared plus 2x minus 4x, that gives me the minus 2x minus 8, giving us two x-intercepts, x equals 4 and x equals minus 2. If y equals 0, x equals 4, and x equals minus 2. Also, if x equals 0, y equals minus 8. Okay. One more piece of information would be useful here, and that is the location of the vertex or turning point of this parabola. We know that the x-coordinate of the vertex can be found by substituting into the formula x is equal to minus b over 2a, where a, b, and c represent the coefficients here. A, of course, is equal to 1, b equals minus 2, c equals minus 8. This is ax squared plus bx plus c. So minus b over 2a would mean minus 2 over 2a, or 2 times 1, giving us the x-coordinate of the vertex is x equals 1, 2 over 2. And then substituting that into the original equation, we can find that the y-coordinate of the vertex is, let's see, when x equals 1, 1 minus 2 minus 8, 1 minus 10, or minus 9. So the vertex, the turning point, is at 1 minus 9, which is over here. We now know enough information to sketch the parabola. We have the x-intercepts, the y-intercept, and the vertex. And it looks something like that. Okay. Let's just quickly go over what we have already here. We have constant functions, something in the form of just y equals a constant. The graph is a horizontal line. We have linear functions, something in the form y equals ax plus b. A and b are constants. And the graph is a straight line. Quadratic functions, something in the form y equals ax squared plus bx plus c. The graph is always a parabola. Okay. We haven't previously seen cubic functions, but I'm going to give you an example now. Just extending the same idea. We've seen linear, quadratic. Now a cubic function will be something of the following form. Cubic function, something of the form y, or f of x, equals ax cubed plus bx squared plus cx plus d, a third-degree equation, okay, where a, b, c, and d are constants. And once again, we will assume here that a is not 0, or else it would just be, of course, second degree, assuming b was not 0. Okay, now I'm not going to get into graphing of arbitrary cubic functions. I do want to look at special cases of the cubic function. The case where b, c, and d are all 0. Special case, b equals c equals d equals 0. In such a case, we get a simple cubic equation, the simplest cubic equation, y equals ax cubed. Okay, I'd like to show you some examples, okay, to sketch this for two different values of a. If a equals 1, you would have y equals x cubed. If a equals minus 1, you would have y equals minus x cubed. By plotting points very carefully, we can show that the graph of y equals x cubed, when x equals 0, y equals 0, when x equals 1, y equals 1, if you plot enough points, you will get a curve which looks something like this. For those of you who go on to study calculus, this curve will come up quite a bit. It has some interesting properties. Okay, right now, let's just say this is the graph of the curve y equals x cubed, a simple cubic equation. It's always increasing. It sort of looks like you're going to form a hill. Okay, but right over here, where you would have sort of turned around and started going down to form the hill, you sort of go up and form a valley. Okay, y equals minus x cubed is very similar to this one. It's just going the other way. It also goes through the origin, x equals 0, y equals 0. But here, when x equals 1, y equals minus 1. So you're down here in the fourth quadrant instead of up in the first. Okay, so these are cubic functions. I'd like to show you now the absolute value function. That is the function y, or f of x, equals the absolute value of x. Now, you have seen the symbol for absolute value earlier. When you first came across it, you were worrying about things like the absolute value of the number 5 or the absolute value of minus 3. We defined absolute value to be of a number to be the distance between that number and 0 on the number line. So if this is our number line, this is 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3. The absolute value of 5 is the distance between 5 and 0 on the number line. Of course, it's 1, 2, 3, 4, 5 units away. The absolute value of minus 3 is the distance between minus 3 and 0 on the number line. Okay, 1, 2, 3. Some people come to think of this as the number without regard to its sign, the fact that the absolute value has to be greater than or equal to 0. It represents a distance. The absolute value of 0, of course, is 0. The distance between 0 and 0 is 0. Working with this idea, we can write down a definition of the absolute value function the following way. By means of a sort of split definition. The absolute value of a number, okay, if the number is positive or 0, okay, trying to describe how to go about finding the absolute value of a number. If the number is positive or 0, well, then leave it alone. You've seen that over here. The absolute value of 0 is 0. The absolute value of 5 is 5. The number is positive or 0, we leave it alone. If, however, the number is negative, less than 0, something has to be done. Now, people tend to say, well, if it's negative, we'll drop the sign. Okay, I'd rather not do that. Instead, what I'm going to tell you is if the number is negative, put a minus sign in front of the number. Now, you may say, what is this? You told me absolute value is supposed to be non-negative, and you just wrote this down as a negative. Okay, look over here. I am telling you, if you want the absolute value of minus 3, remember, minus 3 is less than 0. Instead of dropping the sign, put a minus in front of the number. The effect is the same, right? You still get plus 3. This is what this means. Minus x is not negative because x is negative, so minus x must come out to be positive. Okay, so this does make sense. This is a split definition telling you to do one thing if x is greater than or equal to 0. In other words, if the number is 0 or positive, leave it alone. If the number is negative, put a minus sign in front, okay, which will make it positive, of course. And here we have our definition of absolute value. Using this definition, we will be able to sketch the graph of the absolute value function. Okay, let's see what we have. Because we have a split function, or a split definition, we have to consider the fact that sometimes y is equal to x, and sometimes y is equal to minus x. Okay, so the important thing here is to sketch the graphs of both of these functions, y equals x and y equals minus x. Well, of course, both of these are straight lines. These are linear functions. Okay, and their graphs are straight lines. Y equals x we saw a little earlier today. It is, of course, the identity function. It's a straight line going through the origin. When x is 0, y is 0. When x is 1, y is 1, so on, like so. Y equals minus x is very related to that. If x is 0, y is 0. If x is 1, y is minus 1. If x is 2, y would be minus 2. It would be the line that bisects the second and fourth quadrants instead of the first and the third. Now, how do we put this together to get the graph of the absolute value function? Here is 0, of course. The rule is this. If x is 0 or x is positive, I want you to follow this line. So from this graph, I am going to take this portion. In other words, if x is 0 or to the right of 0, I want you to follow this rule. On the other hand, if x is less than 0 or to the left of 0, then I want you to follow this rule. Putting this together, we get the following. This is the graph of y equals the absolute value of x. When x is less than 0, you are to be following the line y equals minus x. So we will take this portion of the line y equals minus x up to, but not, strictly speaking, not including the origin. As soon as you get to x equals 0, jump off of this line, start on this one, and start following the line y equals x. So it so happens that these two come together because when x equals 0 here, okay, we're at the origin, so we fill up the point that we just missed, and we continue on that line. By the way, if you were, instead of using, say, this formal definition of the absolute value function, just to sketch this by means of a table of values, okay, using a table of values and what you already know about absolute values, for example, let x equal minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, you would get, of course, the same result. The absolute value of minus 4 is 4. The absolute value of minus 3 is 3, 2, 1, 0. The absolute value of these numbers, you leave them unchanged. So you'd want to plot points like minus 4, 4, minus 3, 3, minus 2, 2, minus 1, 1, 0, 0, then 1, 1, 2, 2, 3, 3, 4, 4, and so on. And of course, it continues. So there are two ways of doing this. One is just straight using a table of values. But this type of function, this split function, will come up, okay, time and again. And it's a good idea to sort of get used to it. Don't be too upset if the first time around you found this a little difficult. Okay, it's basically saying this function is composed of two different straight lines which you follow different times depending on what x is. If x is greater than or equal to 0, you're on this. In other words, if you're to the right of 0, you should be on this. If you're to the left of 0, you should be on this. And then we sort of put them together. Okay, the last type of function I'd like to show you today is an exponential function. Okay, by an exponential function, I mean a function of the following form. Y equals f of x is, say, b to the x power, where b is a positive number and it's not equal to 1. This we call the exponential function to the base b. And as a specific example, someplace to start here, I'd like to sketch for you y equals 2 to the x. The exponential function to the base 2. Don't confuse this with x to the second power, or y equals x squared, which of course is a parabola with vertex at the origin opening up. This is not x to the 2, but 2 to the x power. We rule out b equals 1 since 1 to any power is going to come out to be 1. 1 to the first power, 1 to the second, 1 to the third. Okay, so you just get y equals 1, or a constant function there. So we're saying it's an exponential function if b is a positive number, but not 1. Okay, since we don't really know much about this, we're going to sketch y equals 2 to the x by making a table of values. And then we will plot the points. Okay, let's let x equals, say, -3, -2, -1, 0, 1, 2, 3. That's a start. If x equals -3, we get 2 to the -3 power. 2 to the -3 power, from our work on exponents, we know, is the same as 1 over 2 to the third power, or 1/8. Similarly, if x equals -2, we get 2 to the -2 power, or 1 over 2 to the second power, or 1/4. If x equals -1, 2 to the -1 power, or 1 over 2 to the 1 power, or 1/2. If x equals 0, we get 2 to the 0, and of course 2 to the 0 is 1. Okay, any non-zero number to the 0 power is 1. When x equals 1, we get 2 to the 1, or 2. When x equals 2, we get 2 squared, or 4. When x equals 3, we get 2 cubed, or 8. But we can also plot the point when x equals 1/2, we get 2 to the 1/2 power. We know that 2 to the 1/2 power means the positive square root of 2, which is approximately equal to 1.4. That'll enable us to make our graph a little bit more accurate. Okay, let's see what we have here. Okay, we are plotting the point 0, 1. Let's start there. 1, 2. 2, 4. 3, 8. 1/2, about 1.4 up. Okay. Now for -1, we're going to plot y equals 1/2. -1 up 1/2. -2 up 1/4. -3 up 1/8. And if we connect the points, we get something that looks like this. As x gets very large, the y values get very large. For example, x equals 4, y would be equal to 16, 2 to the 4th power, and so on. However, as x gets very negative, what happens is 1 over 2 to a larger and larger power, 1 over a larger and larger number. The result is getting closer and closer to 0. In fact, the negative x-axis is an asymptote for this curve, a line that the curve gets very close to but doesn't quite touch. Okay, and here we have the graph of y equals 2 to the x. This is a typical exponential function. And that brings us to the end of this tape.